Hi, I'm Steve Blackburn. It's a real pleasure to be here, and I want to start by thanking Stefan and Christos for inviting me to give this talk. And before we go any further, I want to introduce you to an Australian tradition that when we give a talk, we acknowledge the people on whose land we're giving the talk. And I know this is virtual, and I know that you're going to be scattered all around the world, and I know that I should be in Manchester, England, but COVID being COVID, I'm actually here in my home in Canberra, Australia, and I want to acknowledge the people who have lived here for thousands of years. And this rock painting behind me right here is an example of their history that goes back in this very place thousands of years. These rock paintings are in the hills just outside of the city, and I can actually see those hills and where those rock paintings are from the balcony of my house. And this is a reminder of the thousands and thousands, or 25,000 year long history at least, of the people who've inhabited this land before us. And so I just wanted to acknowledge that before I start my talk and introduce you all to an Australian tradition, which I think is a good one. So here I am. I'm in a workshop apparently, and I'm going to talk to you about toolkits. And specifically, I want to talk to you about MMTk, which is a toolkit that I've played a part in developing. And I'm going to tell you a little bit about why it was developed and the history through which it got developed. And I'm hoping that through doing that, you're going to learn a little bit about the technology of garbage collection, but also about research, the way research happens, and about the social dimension to building a system like this. So before we go any further, I'm here with my friends, the horse and the garbage collector guys, and what they're doing is they're collecting garbage. And I put this slide up here to remind people that garbage collection actually is, in computer science terms, a pretty ancient technology. McCarthy and Collins published their famous papers in 1960, and we've been working on it ever since. Some people might say, hey, it's such a mature area. What's interesting to study there? Well, one of the fascinating things about garbage collection is that it depends so much on the language and on the underlying architecture and on the demands of the users that they place on that language. And therefore, it is something that is very sensitive to the context it's in. And that context is changing and has changed radically from the days when McCarthy and Collins first built garbage collectors. So, yes, they built garbage collectors and they solved some basic problems way back then. And other greats of computer science, people like Dijkstra and Steele, and these people have contributed mightily to the development of garbage collection. But fortunately for us, there's still much, much, much more work to be done. And that's because garbage collection is finding itself in new places. It's finding itself in our phones, of course, which would be unheard of to the likes of Collins and McCarthy. And it's finding itself on servers, in games, in all sorts of places. And as it does this, it places new challenges and creates new challenges for us as researchers, either in academia or in industry, to make our garbage collectors perform better. I'm going to start by just saying a little bit about garbage collection and security. Now, I know with the MPLR audience, I'm to a fair extent preaching to the choir here when I say that memory-safe languages are a good idea from a security standpoint. They avoid use after free bugs because they have garbage collection, so you're not going to free something that might still get used. And they also avoid buffer overflows because they've got checks, balance checks and so forth. So these are some of the great things about memory-safe languages. However, there's an assumption here, and that is that we've implemented the memory-safe language safely. And that's part of what I want to talk about today. And if we look, we can very quickly find there are more than one example of serious security issues that are due to problems in the implementation of the garbage collector. So we've got a secure language, but the implementation may not necessarily be secure. And of course, this gets more troubling and more difficult as our garbage collectors are more complex and as our hardware gets more complex. So can we build more secure GCs? I think this is a really interesting question. I don't have any great answers to that just yet, but I think it's a very, very interesting question. I think that's one direction that my research is currently heading towards. I saw an interesting talk this year. In fact, it was at the start of this year, where someone made the claim, the very strong claim, that performance is the enemy of security. Performance is the enemy of security. And the argument they make goes something like this. Performance begets complexity. If you want something to perform well, it's going to be complex. And once something's complex, then you have a lack of understanding. And a lack of understanding lends itself to insecurity. Therefore, so the reasoning goes, performance leads to insecurity. Now, if you look at something high performance and complex, like this jet engine here, you get the sense that, yes, when you want to engineer something for performance, very often it's hard to do things without complexity. There's a lot of complexity here. And it's easy to get overwhelmed by that complexity. And in fact, if we go and take a look at the source code for garbage collectors in 3 of the well-known runtimes today, on the left there you've got V8, in the center you've got OpenJDK, and on the right there you've got .NET. You'll see real indicators of just how complex they are. If you look at V8 there, you'll see we've opened up the heap folder there, and you can see some of just the very beginnings of the code that sits in the heap folder, which is where the garbage collectors are. And so just a quick glance at that gives you a sense that the garbage collector, which lives in this folder here, is not a simple creature. And in the middle there, we've got G1, which is one of the garbage collectors that lives inside of Hotspot, one of the most mature ones. And only some part of the files in that folder are visible in this screenshot, and you get a sense of just how complex the G1 collector is. And then finally on the right there, we look at .NET, and we see .NET, in fact, it's just one file there, which is the gc.cpp, and GitHub won't show us the contents of the file because it says that the file's too big. It's a very, very big file. It's a very, very complex thing. So again, I just want to impress upon you, here we have 3 excellent examples of high performance, very carefully engineered pieces of software that are undeniably complex, which would tend to lead to support the argument that performance is the enemy. However, I want to challenge that. Now, I think most of us would agree that complexity leads to a lack of understanding. Almost by definition, complexity, that's almost a matter of definition. And similarly, lack of understanding will lead to insecurity. I think that's pretty uncontroversial. But I want to challenge the first question, first statement that says that performance begets complexity. I'm not sure I buy that. And I want to make it a case to you right now that that may not be so. And I want to do it by invoking Fred Brooks. Now, Fred Brooks talked about essential complexity and accidental complexity. Essential complexity and accidental complexity. And the idea is this. It's a really nice idea, and it's a very important idea if you're building complex software like this. And that is, when you're trying to solve a problem that is complex, such as building a jet engine for an airliner, or building a garbage collector for an industrial strength system that's going to be under significant load and run on very complex hardware. When you're building a system that is complex like that, the software, the solution, will have a level of essential complexity. That is a consequence of the complexity of the problem. So there's an essential level of complexity in the problem itself. However, most software systems add to that a significant amount of what Fred Brooks calls accidental complexity. And accidental complexity is where we have the problem. So none of us who know anything about garbage collection would suggest that a garbage collector is anything simple. Okay? A realistic industrial strength garbage collector is not going to be simple. However, my suggestion is that the way we build garbage collectors is often riddled with accidental complexity. There's a lot more complexity there than we need. I'm going to go further and suggest sometimes that's an artifact of the choice of language in which we implement the garbage collector. So the statement that I heard at the start of the year was the performance is the enemy of security. And I would argue, in fact, complexity is the enemy of security, and complexity is the enemy of performance. And again, we go back and look at this and we can see once more that we've got this very, very complex systems. And what I want to point out, though, is that these systems, although they are very, very impressive systems, they are not ones that change very fast. And in fact, the time it took from the G1 paper to being published to being the default collector was very, very considerable. And these things are remarkably stable, which of course is a good thing. But also, we have not seen a lot of innovation in each one of these things. I'm going to say more about that later. But I want to put it to you that sometimes what happens is you design something very good, very interesting, like the G1 collector or like the collector in V8, and then you engineer it like this, and find yourself in a position where it's very hard to move forward. And so what you tend to find is you're at a local minima, and it's very hard to escape that local minima because of the inertia generated by the complexity of the software you've created to solve your problem. So I saw this a while back, understanding the JDK's new super fast garbage collectors. And it talks about ZGC, Shenandoah, and improvements to G1. And of course, there's also the Azul collectors. What struck me here, though, is the new super fast garbage collectors. They are fast collectors, they're impressive collectors, but they're not particularly new. Each one of these collectors has made minor changes to themselves over time. So, and not only that, they have their roots in some key ideas that go all the way back to Lang and DuPont, which is the algorithm on which the G1 algorithm owes its heritage. Okay, so there's some fundamental ideas here which actually haven't changed very much over time. Now, that in itself is not a problem, because it's entirely plausible that this fundamental idea and the fundamental ideas behind G1 and the ones that were then refined in the C4 collector and in Shenandoah and in ZGC, those ideas, the path they hold in common, are about the way the heap is structured, and maybe that heap structuring is fundamentally the right way to build GCs. And so we're going to see this heap structure repeated again and again into the future. The alternative point of view, though, is that we find it very hard to be innovative on a grand scale because of the inertia created by the complexity of our software. And I'm going to suggest to you that's part of the problem we have here. And the similarity between these algorithms, although they have a lot of innovation at the mechanical level, there's no question about that, the similarity, the underlying similarity between these algorithms, I think is striking, and I think it says a lot about the difficulty of doing wholesale innovation and really creative work in industrial garbage collectors. So now I'm going to move on to a different topic. I'm going to talk about the Memory Management Toolkit, which is something I helped develop with Catherine McKinley and Perry Chang over a period of years. And so at this point, I'm going to talk about the history of that project, how we got to there, and what it gave us. The story starts in Amherst, Massachusetts, in the fall of 1999. In fact, it's in October of 1999. So 21 years ago. And I just arrived as a new postdoc at UMass. And at that time, I had, in fact, there's a backstory here which is quite interesting as well. I had visited the campus, I think about a year before, and to see if I wanted to do a postdoc there, and to also check out options for my wife, who was also going to do a postdoc. And I visited that campus, and the day that I was there was a talk being given by from IBM Research. They had this thing called the IBM Research Day, and they came to UMass, and there was a person there called Vivek Sarkar, who was talking about a new VM they were developing in IBM Research, which was extremely interesting. It was a VM targeted at high-performance servers, highly scalable VM. And one of the interesting quirks about this VM is that the VM was for Java, but it was also written in Java. And later on, this VM would come up again in this trajectory of the story I'm going to tell you. But I found it very, very interesting that just by chance, the first I heard of it was on the day that I visited this campus to test out whether or not I should be doing a postdoc here. And I decided I would do a postdoc here. And when I arrived, I soon found myself working with Elliot Moss, and Catherine McKinley. Catherine at that point was on sabbatical at the University of Texas. Elliot was there, and I was working with Elliot on a VM he was building. Now, you might ask yourself, why was Elliot building a JVM? That sounds like an expensive thing to do. Well, you're absolutely right. It is an expensive thing to do. However, at that time, there were no open source JVMs available, at least not ones that were performant enough that you could do serious research in them. And so Elliot had set about, with his students, building a new JVM that would allow them to do high performance Java research. And my job as a new postdoc was to look at porting that VM to the alpha. And I can still vividly remember, I think it was my very first day sitting down in that lab, having been introduced to the students and explained to them my background in systems programming and so forth. And one of the students, one of the newer students, coming up to me and saying that they had a bug. And I said, "What's the bug?" And they said, "The compiler's broken." And I thought, okay, I'll come and have a look. And yes, indeed, GCC had segfaulted. Why had it segfaulted? Well, it had segfaulted because they were using macros, which is what you do when you're writing C code. They were using macros to get performance in this VM, and the depth of the macro nesting had blown some internal limit in GCC, and it caused the compiler to crash. It took a while to debug, but that was the first time I'd ever seen GCC crash. And that made me think a little bit about the way we were building our VMs. And we felt compelled to build it that way because we needed the performance. Anyway, let me move on to another part of the story, which takes us closer to MMTk. Right at the time that I arrived, OOPSLA was on in Denver, and just a few weeks later. And Darko Stvanovic, who you can see this lovely photograph of him there. Darko, I don't know when that photograph, I think he's skiing. Darko was a PhD student in the lab, and he'd just finished. And he'd done some really remarkable research, and it was on the design of GC algorithms. But what's interesting about it, and perhaps surprising for younger folks, is that the way he'd done it was that he'd generated traces of real programs running on a VM, and he'd done that as an intern at Sun Labs. And he built these traces. Then he'd gone back to the university with those traces, and in the university, he'd built models for the performance of things like the tracing loop, the write barriers, and things like that. And then he was able to design new GC algorithms and estimate their performance using these models, these performance models, and the traces that he'd gathered. Anyway, I was sitting in the lab one day, and I got a phone call from Catherine. And Darko had just given his talk in Denver, and she was calling me from Denver, and said that asked me if I was interested in working on a new JVM. And what had happened was, at the end of Darko's talk, someone from IBM Research, that's Mark Wegman, had approached Catherine and had asked Catherine why it was that Darko was using a model of GC performance and why he wasn't using a JVM. And the answer was very simple. He didn't have access to a performant JVM because they weren't open source. The ones at IBM and at Sun Labs were all closed source. And the only time he got access to it was when he was an intern there. So, and Mark said, well, actually, we're about to release and make available via open source a new JVM. It's called Jalapeno. It's Java and Java. And of course, that was the VM that I'd heard Vivek speak about a year earlier. And Mark asked Catherine if she was interested, and Catherine said, of course. And that phone call, of course, was one that changed the course of my career, because I responded to Catherine with excitement and said, yes, I'm absolutely want to follow that. And sure enough, before too long, I was down at Yorktown as a temporary IBM employee doing the first port with my student, John Zigman, doing my first port of JXRVM to Linux so that we could take it back to the lab and we could accelerate the process of open sourcing it. And so it was that I started working with what was then called Jalapeno, which later became known as JXRVM. And the first thing I did was look at the garbage collector, because we're in the lab. Elliot and Catherine and I were all working on garbage collection, and that was my focus. And so the question was, can we do our garbage collection research in there? Well, at the time, in that initial release of, well, it wasn't actually a release, in that repository, there were garbage collectors there. There were a handful of them, but each one of them was a monolithic instance, and they were literally a single source file. They were in Java, because of all of Jalapeno was in Java. And, but they were written in a fully static style. So they were essentially written in the style of a C program. There was no object orientation, and, so they were monoliths. And so the question was, can we do things, more flexibly, more generally than that? And I set about, with Catherine and Elliot, designing a new toolkit, which, we started calling GCTK. But not long after that, we had meetings with the folks at IBM and, started collaborating with Perry Chang. And Catherine and Perry and I embarked on building a new toolkit, which we called MMTk. And this would be the thing that I subsequently spent a large part of my research career working on. And we did a number of interesting things in building that. But I think perhaps the most interesting one was that I remember Perry as being very determined that we should have faith in our colleagues who built the runtime, and in particular in Dave Grove and the other folks working on the compiler, that we should assume that any code that we wrote in idiomatic Java would be appropriately optimized. And therefore, we should build our GC toolkit as far as possible using natural idiomatic Java, which was in opposition to the approach that had been taken previously, where they said, okay, we're going to write this as if it's C code because we don't know what the compiler is going to do with it. And so this approach and the idea that, well, if the compiler doesn't do the right job, then we'll get Dave to fix the compiler, or we'll fix it ourselves, or if all else fails, we'll write the code a different way. But that'll be our path of last resort. And so it was, we built MMTk and tried very, very hard as we did so to build it in as natural way as possible in terms of the coding style. And so what did we end up with? Well, it was written in a high-level language. It was a fully static dialect of Java. The reason why it was fully static is because we could not call new. We couldn't call new because you'd go into infinite regress if you called new inside of a metacircular Java garbage collector. But we apart from not being able to call new, we tried to use the language as fully as we could. And one of the other things we did was make use of Java's strong typing. And we introduced special types to help us do things like identify an address. So we had an address type, which is roughly a void star, an object reference, which was guaranteed to point to the start of an object, and so forth. And we used the type system to help us debug the code and help us gain confidence that our code was correct. The other thing we did was we made very heavy use of assertions. The code was very modular, so we made a great deal of reuse of code. So wherever possible, things like an allocator. So you had an allocator, we had a reference counter collector and a mark sweep collector. They both use the same free list allocator. So we reused the code that did the free list allocation for both of our collectors. Bump pointer allocators used by many different collectors. Things like the work queues and so forth used by many different collectors. All those things, those mechanisms, we optimized those as far as we could and reused them as much as we could when we built new GCs, which meant that the code that was dedicated to actually writing the GCs was actually quite succinct. And we built a lot of debugging features in. So we had things like what we call the sanity collector, which was a ground truth collector, which we had a lot of confidence in, which would work on the side if it was enabled. And it would allow us to check the liveness of anything as reported by our new GC we're developing, and check that against the sanity GC, which we regarded as a ground truth. And that was extremely useful as well. When we finished building MMTk, we wrote a paper. We actually submitted the paper. It was a very big paper. We submitted it to OOPSLA, and we're very disappointed that it got rejected from OOPSLA. But there was a silver lining on the cloud, because one of the reviewers said, what you really need to do is split your paper in half and have one half be about the software engineering this system and the other half the analysis you did with your system. So we did that, and we wrote this paper here, which we submitted to ICSE. And this paper here simply looks at how we engineered a high-performance garbage collection framework using Java. Which at the time was considered a little bit surprising, because people didn't think you could use Java to build something as performant as that was doing low level systems programming. There's some interesting results in there. This is an example of one of the results in there. This table here reports a bunch of software engineering metrics with respect to two different versions of the original IBM collectors. We call them here the Watson 2.0 and the Watson 2.2. And you can see there are four collectors there: the semi-space mark sweep, generational copying, and generational mark sweep. And then we replicated those in MMTk. We built the exact same four. But one thing you'll notice if you've got sharp eyes, there's a fifth row there for MMTk, and that's generational, because what we've done there is we've factored out the elements that are common to the generational copying collector and the generational mark sweep collector in a separate class called generational. And you'll see here the numbers of non-comment source code lines is roughly half, even when you take into account that extra generational file. So we've simplified it significantly, and that is after they had simplified. They did a lot of refactoring. The code at Watson had been developed by professional staff engineers who'd built a lot of production code. And but they did do a lot of refactoring between 2.0 and 2.2, and you can see here that even with that refactoring in place, the MMTk code was substantially simpler. And over on the right here, you see another software engineering metric, which is the cyclomatic complexity metric. And again, you can see that it's nearly twice half the complexity of the Watson code. So that's one example of what we did. So we're building a system which, according to software engineering metrics, is significantly simpler. But we managed to do this without sacrificing performance. And if you look at this graph here, you'll see on the y-axis, you've got time, and on the x-axis, you've got heap size. So we're adjusting the heap size and measuring the performance. And the dark icons are the new MMTk collectors, and the hollow ones are the Watson ones. And I notice here there's actually a typo. We've called it JMTk. That's because for a short while we were calling it JMTk instead of MMTk, J standing for Java. And somehow or other that slipped through the checking in the paper. But anyway, this is straight out of the paper. But what you'll see here is that if you look at those circles, the hollow circles and the dark circles, you can see that even though we've got substantially simpler code by objective measures, it's also performing significantly better. And likewise with the semi-space collector, which is the hollow squares and the filled-in squares, there's a significant performance gap between our new simpler collectors and the original ones. Why am I showing you this? I want to remind you of the statement earlier about performance and complexity. I'm arguing here, I'm trying to use this as a concrete counterpoint, that here we have something which is significantly simpler by objective measures. It's roughly half the complexity, and yet it's performing significantly better. And these are the same algorithms. We've got semi-space and mark sweep. They've got the classic algorithms. We're performing substantially better. So I'm trying to make the case here that particularly when you're building something like a garbage collection toolkit, you can make things substantially simpler and yet not sacrifice performance. The other thing we did was write the second paper, which we sent to Sigmetrics, which 10 years later won the Test of Time award there, and where we went and use the framework to do a lot of analysis. And that was actually a lot of fun. And we found out all kinds of things there that until that point had been often subject to, essentially folklore. And we're able to concretely measure them because we could compare algorithms, one algorithm with another, holding everything else constant, holding the compiler constant, holding the whole of the runtime constant, holding constant even the lower level mechanisms of the GC. So that allowed us to actually compare the algorithms. And we could do things like look at the locality difference between a mark sweep collector and a semi-space collector, just for example. And this graph here is one of the more fun ones in the paper. And you see here all 6 collectors we had there. We've got the semi-space, mark sweep, and reference counting, and the 3 generational counterparts. And the only thing I want to highlight here is this interesting point that you see between the semi-space and mark sweep. You see a crossover when the heap size gets to a particular size. And you see here when the heap size is small, it becomes more worthwhile to have a mark sweep collector, which is the circles, than to have the semi-space collector, which is the squares. But it's a crossover because once the heap size is bigger, the space inefficiency of semi-space matters less. And what matters more is the fact that semi-space has better locality. And the difference is actually fairly significant. But what's interesting is that if you look across these 3 different microarchitectures, over here we've got the Pentium 4. This was a long time ago. In the middle we've got an AMD Athlon. On the right we've got an IBM PowerPC. You'll see that this point shifts. So it's a microarchitecturally dependent point because it depends on how locality affects this particular microarchitecture. So I found that quite interesting. And that's the sort of thing we could do once we had a framework where everything was held constant except these high-level algorithms. It allowed us to do this sort of apples-to-apples comparison, which gave us a lot of new insights into how we might build garbage collectors. We went on and did a lot more like that. And I'd classify this work here as what I'd call discovery, which is essentially exploring not new algorithms, but understanding much better how existing algorithms or new mechanisms might make existing algorithms perform better. And we published a lot of things, looking at things like how the performance of write barriers works, how different write barriers perform, how zeroing works. There's a great paper in that stack there from Si Yang on the performance overheads associated with zeroing. We did a lot of studies like this, and MMTk allowed us to do that quickly and allowed us to do apples-to-apples comparisons. And in doing so, it often gave us insights into how we might build new algorithms. So this is one of the real benefits of a framework like MMTk, is that we could do studies like this, and we did a lot of such studies, and I think they helped the community. we're also, of course, able to be creative. And here there are a few examples of new algorithms we've built, completely new algorithms that we built inside of MMTk, which changed the performance in interesting and creative ways. And we're able to build them surprisingly quickly because of the modularity of the MMTk framework. But the question is, how much impact did this actually all have? And as researchers, whether you're an academic or an industrial researcher, you probably care most ultimately about how much impact you're having. And this is where we all need to stop and think for a bit. And it's not always as good a story as I would like. And in fact, if we look at all that work I just showed you, and I reflect on where it's really had a direct impact, I can see just two language implementations that have directly taken on garbage collection algorithms that we developed. And that's the Scala Native and Inco, which both use Imix as the garbage collector, which is fantastic. But also, I think, to be totally honest with you, that's a little disappointing. For all that work, I might have expected to have had more impact on the way production garbage collectors work. And so the question is, why did we not have more impact than just this? And that's what I'm going to reflect on now, is what are the barriers to impact? First, and perhaps most important, credibility. Work needs to be done within an industrial strength runtime for it to be considered credible, both by our fellow academic researchers, but most crucially by our industrial colleagues. If we're not doing our work in an industrially credible setting, then we won't gain the attention of people who might want to transfer it. Now, I can dismiss it as being something that is curious, interesting perhaps, but not something they're going to invest time in. And the story with MMTk was that at the beginning of the story, when we were using Jalapeno and Jix RVM, it was a very fast runtime. In fact, it was within 5% of the production JVMs. And so we had credibility absolutely on our side. But as IBM pulled funding from that project and they moved on and did other things, the project gradually slowed down and it slipped in its performance, eventually slipping quite significantly. And so this credibility disappeared, and then we were robbed of the opportunity to do research that had really obvious credibility in a way that we found compelling. And the problem there was that MMTk was written in a dialect of Java inside Jix RVM. And we couldn't move it outside of that context. So we were stuck inside of a context which was gradually diminishing in terms of its impact. But another question is that of transferability. And that is, can someone outside of our particular context see the utility in what we've done? And that's not going to happen if you're only working in one runtime with only one language. So ideally, what we can do is take our ideas and show how they can translate across language runtimes. And again, that's something that we couldn't easily do with MMTk because it was stuck very much in that one runtime. So in the last part of the talk, I'm going to talk about where MMTk is now. And the good news is that we've actually completely rewritten MMTk, and you at MPLR are the first to hear of it. We've just released it this very week. We've done a full rewrite of MMTk in Rust. It presents itself as a shared library with VM-specific bindings. In terms of credibility, we've been doing this work with close cooperation with product teams. And in terms of transferability, we've got implementations in Jix RVM, OpenJDK, and V8. And we're already working on a couple of other languages. Why did we use Rust? Well, it goes back to a paper that we wrote, my student E. Lin wrote a few years ago at ISMM, where we did an exploration into building a garbage collector in Rust. And what we found was that the static safety guarantees of Rust were actually extremely helpful in building the GC. And the number of times we needed to break Rust safety were actually very limited. So we're getting the safety with very few places where we needed to break Rust safety guarantees. And we did all this with great performance results. So that experiment gave me a lot of confidence that if we moved to using Rust for MMTk, we would have a better performing system and one that we had a lot of confidence in the correctness of it. So what would be the motivation for industrial partner or an academic researcher to use MMTk with their runtime. So for an industrial partner, the way I see it is that the motivation for them is that it allows them to engage with the research community that they might, in a way that they might not otherwise be able to do so. So if they have an MMTk binding to their runtime, then many people from the memory management research community, whether or not they're using this industrial partner's runtime, can engage with it because the binding's there for free. So if I go and build a new GC algorithm, I can automatically go and test it. So if I build a new algorithm, I can go and test it in OpenJDK. I can test it in V8. So there's a vested interest for someone who's maintaining a system like V8 in allowing and opening it up to the research community by supporting a binding to MMTk. It also, more selfishly, allows them to evaluate research ideas that come out of the community on their own terms. So if a researcher produces something in MMTk and the binding exists to their runtime, then it allows them to evaluate that researcher's ideas using their own setting and using their own workloads. And from the standpoint of the academic researcher, it allows them to conduct research in an industrially credible setting. So you can work with OpenJDK, you can work with V8, and it gives you greater visibility because you're not just demonstrating your algorithm in one runtime, in one language, but in multiple languages and multiple runtimes. So how complex is it? How do we deal with the complexity in MMTk? Our approach is relatively simple. We think of things in terms of 4 discrete units. On the left there, you see the runtime, which in this case is V8, and that's an upstream thing. We don't touch that. Ideally, we don't touch that. We might need to at the beginning. And on the right, we see MMTk, and that's the core of the garbage collector. And in between, we see 2 impedance matching pieces of code, which we call the binding. And the one on the right is written in Rust, and that contains code that is specific to V8, but is in hot paths in MMTk. So for example, if we wanted to trace objects, find all the references in an object rapidly in MMTk, we can write code here in the Rust binding there, which introspects into V8 in Rust and tells us where the pointers are because it's got particular knowledge of the way V8 organizes its objects. And there's no impedance problem from the hot code paths in MMTk that want to establish that. On the other hand, the code on the left, that wedge on the left there, allows V8 to have its hot paths of things like write barriers, allocation sequences, and so forth, written in C++ and inlined into V8, only calling out to MMTk on the slow path. So this is how we've built it. And we've done this not just for V8, but also for OpenJDK and also for JIX-RVM. Now, I've put the slide here because I wanted to talk briefly about my stay in Munich. I had a fantastic stay in Munich at this time last year. I think I left in November and I spent 3 months there. And it was an absolutely beautiful place to visit. And I worked with a fantastic team. That was the V8 team who are based in Munich. And I took this photograph here at the Olympic Park, and you can see the Olympic Stadium there. And that beautiful piece of concrete there on the left is actually a fantastic path that I ran along many, many times. And this brings back great memories. But the reason why I'm mentioning this is because one of the things I did while I was there, I did a couple of things, but one of the things I did there was further the work that had been done by one of my students in developing a binding from Rust MMTk to V8. And so what I was doing is trying to get that and then upstream the binding. And as I said before, V8 is a complex beast. And this here is a snapshot of the first CL that I developed. And you can see 82 files. It's touched 82 files. And I'm putting this on the screen here just to give you a sense of what it takes to stub out all of the GC relevant parts of a runtime like V8 so that we can intercept them all and bottleneck them through to MMTk. And this is only the beginnings. We end up being the change is actually quite a lot more substantial than this in the end, and it's now upstream. So if you go and look at the V8 source code, you will see the third-party heap, which was written by me and my students. And I put this here as a just more or less for fun. This is me having a debugging session, and it actually brought back echoes of that very first day at UMass. Because here I was trying to debug something deep inside of V8, and I find that I'm on line 88 on the right there. And of course, what is it? It bottoms out into some non-trivial macro that actually very helpfully raised an assertion check. But I'm putting this here to, again, illustrate the complexity of working in a C++ code base that is very mature and that has a lot of built-in complexity. So status, you can get MMTk right now from GitHub. We've got ports to 3 different VMs. And the functionality, there's a lot of functionality there. The actual release only includes 2 collectors, but we've built a lot more collectors, including a family of collectors for G1, and demonstrated them as being performant, and we'll have them public as soon as we can. And with that, I want to finish up. And before I do, I want to say some thanks. One of the things that I found actually really enjoyable about preparing a talk like this was going through and thinking through all the people who are involved in the various aspects of that work. I've talked to you about 20 years worth of work there in building up a whole lot of GCs, and in doing so, I collected the names of the different people I've worked with, and I've put them on the screen there as an acknowledgement of just how much these different people have helped me, and how much this something like MMTk is the product of an enormous amount of work from a very large group of people. And with that, I'll say thank you, and I'll be very happy to take questions.